Hi everybody. So I know this is a little weird, but we're gonna be adaptable and flexible, and we're gonna find a way to succeed no matter what's happening in our world right now. So I'm going to be doing our lectures through PowerPoint with recorded video and audio on my end. I've done this before for other classes and it worked well, so let me know if there's anything that I can do to improve it, especially if you're having any audio issues. But in this video we're going to cover the first half of Chapter 6. So Chapter 6 is called Chemical Reactivity and Mechanisms, and the first half is really a review of second semester general chemistry. So we're going to talk about energy diagrams, kinetics and thermodynamics, and I know that that's a big section of second semester general chemistry, so we're not going to talk about everything from that semester. We're going to pick out the important stuff and hopefully refresh your memory on it, and then also relating it to organic chemistry. So we're going to start with the thermodynamic side, and then we'll switch over to kinetics, and then we'll kind of put the two together and see how we can look at both of them at the same time. So the big part when we talk about thermodynamics is to talk about enthalpy. And enthalpy is a measure of energy in the form of heat, and it gets abbreviated with an H. We also see it abbreviated with a Q, so if you remember back to the equation Q equals mc delta T, technically Q can only be used if we're at constant pressure, but rarely are we not at constant pressure. We're normally just at atmospheric pressure. So generally H and Q are interchangeable. The official definition of enthalpy is it's the exchange of kinetic energy. And for us, that means the energy needed to break a bond or the energy released when a bond is formed. So this is also called the dissociation energy. And when you took general chemistry, you learned 5 or 6 different ways to calculate this value. Again, we're not doing the math behind this. We're going to look at how to evaluate an energy diagram or a reaction and decide if delta H will be positive or negative. And so our big thing is that when we break a bond, delta H is going to be positive if we're breaking a bond. Oh, you gotta be patient with me. I did buy a pen mouse so I can do this a little faster, but it won't be here till Friday. All right, and delta H will be negative if we are forming bonds. All right, 2 types of reactions down here. We have homolytic bond cleavage. So we know that homo means same, and so that means, for this specific example, it means how the electrons are moving. And if we're treating the electrons the same, that means that in this bond right here, one electron is going towards the Y. So we have this arrow right here. Notice the end of the arrow right here. It's called a fishhook arrow. It just has one side on it. That's telling us that it's showing the movement of just one electron. And then because a bond is made up of 2 electrons, there's the other electron. So meaning that we're treating these 2 atoms the same. That's the homolytic part. And bond cleavage is just another way to say bond breakage. So when we say homolytic bond cleavage, it means that the bond is breaking evenly between the 2 atoms, and as a result, we're going to form 2 radicals. You remember back, a radical is when we have that unpaired electron. Now, this is not common. We will have one chapter dedicated to this type of reaction, but the majority of the time, we're going to talk about heterolytic bond cleavage. And so with heterolytic bond cleavage, we know that hetero means different, and so that means our 2 atoms are going to be treated differently. So there's our bond made up of 2 electrons. Our arrow here is the arrow we've been drawing, the regular style arrow. and it's showing the movement of both of those electrons. So in this case, they're both going onto that Y atom, and none of them are going onto the X. So the two atoms are getting treated differently, hence the hetero part of the name, and as a result, we make two ions. So the X is losing its electrons, so it becomes positively charged, and the Y is gaining those electrons, and it becomes negatively charged. Oh, I went back. Let's see if there's anything else on there I needed to talk about. Oh, there was, okay, two more things. Another way that we can label these is that our endothermic reaction, we can say that it is reactant favored. It's going to take some skills. All right, and our exothermic reaction, we can say is product favored. And this has to do with which substance is lower in energy. One last thing about this section is that if you're learning the same information in a physics class, the signs are going to be opposite. And the reason for that is in chemistry, we focus on the system, and in physics, they focus on the surroundings. So it's the same information, just looking at it from two different perspectives. So I just want to bring that up because it can be a little bit confusing if you're taking both classes at the same time. So the next type of energy we're looking at is entropy. And if you remember back, this is a type of energy that is measured by disorder, or sometimes we say chaos. And it's the second thing we look at to decide if a reaction will be overall spontaneous. And in order for a reaction to be spontaneous, the delta S needs to be positive. Or another way to say that is that the entropy is increasing. And another way to say that is that the disorder is increasing. So there's a couple ways that this can happen. We can increase the number of molecules overall. So right here we have one molecule and we end up with two individual molecules. So because we increased the number of molecules, the disorder can increase. Another one is a ring opening. So here we have a ring molecule, and when this bond breaks, it creates an acyclic compound or a chain compound. And so because it has more freedom of movement, it's going to be more disordered. Another way that this can happen, and it's similar to this one up here, but if we go from a molecule to ion, so if we go from a molecule to a cation and an anion, we are also increasing the number of items, but that's another form of this. And then the last one is if we do a phase change. So if we go from a solid to a liquid, or a liquid to a gas, those are all positive entropy increases because we're allowing for more movement, more disorder. So let's look at a practice one here. So our question says, will the entropy in the following reactions be positive or negative? So in this first reaction, we have a chain with a double bond on each end. It's telling us that we're using a metathesis catalyst. Not really important, just telling us it's something that's going to help the reaction. And we're going to end up with this cyclopentene. Now, this is the opposite of our example on the last slide. So because we're going from a chain to a ring, it's going to have less freedom of movement. So our delta S is going to be negative because the entropy is decreasing. In the example down here, we have a tert-butyl group attached to a halogen, to a bromine. Our arrow here is showing us that this bond is breaking, and so we end up with a carbocation and a bromide anion. So our delta S in this case is going to be positive. We're increasing the number of species or items within our solution, and so that's going to have more disorder. When we put delta H and delta S together, we get delta G, which is Gibbs free energy. So Gibbs free energy is a measure of all of the energy. And what we're looking at here is the same types of energy diagrams. Really, the only thing that's different here is the terms. So we're using the term exergonic and endergonic. That first part, the X and the end, are still the same. It's just slightly different wording because we're using delta G instead of delta H. We also have up here, it tells us that if delta G is negative, then it will also be a spontaneous reaction as well as exergonic. And if delta G is positive, it will be non-spontaneous or endergonic. So the last one within our thermo category is looking at K, our equilibrium constant. And this equation, or this diagram here, is incorporating G, our free energy, with the concentrations. And because K is a ratio of those concentrations, it's really putting those two pieces of information together. We know that low energy is good, low energy is stable. So at this point right here, this is the lowest value that G can be, and at that value is a representation of our concentrations of our reactants in our products. So if our delta G was right here in the middle, that would mean that our that our reactants in our products would have equal concentrations. But because it's over here, that tells us that the concentration of C and D is greater than A and B. C and D are our products. So that means because our delta G falls over here, that our K is going to be greater than 1. So let me grab my little pen here. So I'm going to call this the middle. I'm approximating. Oh, my mouse could drifted a little there. All right, so if we're on this side, then that means our delta G is going to be negative. We can also say that K is going to be greater than 1. And we can also say that it's a product-favored reaction. And if we're on this side, we can say that delta G is positive and K will be less than 1, and we can say that it's reactant favored. Now over here on this side, the one more label that we could give this is that it's spontaneous. And something to add to that, a reminder, spontaneous does not mean fast. So sometimes we think of spontaneous as explosions, which can very well be true. But the formation of rust is also spontaneous, and that's definitely not a fast reaction. So just something to keep in mind, because over to kinetics. And if you remember back to learning about kinetics, this is the equation that we first learned, that the rate is equal to the rate constant times the concentrations of our reactants, and then they're raised to some exponent, which is our order, and that has to be figured out experimentally. So again, we're not doing the math behind this, but we do want to remember this information down here. This is telling us how those rate orders affect the rate. It's really telling us how sensitive the rate is to concentration changes of our reactants. So here's our equation. How will the rate change if the following concentrations are made? So we have the rate is equal to our rate constant K times the concentration of NO squared times the concentration of H2. Just a quick reminder, remember when we have those brackets, that means concentration, and usually it means molarity. So the first one is that the concentration of NO doubles in concentration. And so if this happens, our rate will quadruple, or will go up by 4 times. And the way to think about that is that if this is twice as big, well, we're raising that to the power of 2. So 2 squared is 4. So our rate will be 4 times as large. So what if the concentration of NO is cut in half? Our rate will be cut in fourths. So kind of the same thing. If we have 1/2 raised to the power of 2, we're going to end up with 1/4. So our rate will be 1/4 the speed. What about our other reactant over here, H2? What if we triple the concentration of H2? Well, our rate will just triple. Because the rate order of the hydrogen is just a 1, it doesn't have an exponent on there, the change in concentration and the change in the rate will happen, they'll be directly related to each other. So the other part of that rate law is the rate constant, and there's 3 main ways that rate constant, or there's 3 main things that will affect that rate constant, and the first one is the activation energy. And so normally we think of activation energy as this hill, and so in a faster reaction we have a smaller activation energy, or a smaller hill, which means that we will have a large K value, because that's telling us that it's going faster. And then when we have a larger hill, a larger activation energy, it will be a slower reaction, which means we will have a smaller K value. And what this hill represents is how much energy it takes for the reaction to occur, for the collisions to create a reaction. The second thing is temperature. A higher temperature means more energy is given to the molecules, which means they can move around at faster speeds. When they move around at faster speeds, they're going to hit each other more often, and they're going to hit each other at a harder force. So that's going to result in a faster rate, which will give us a larger K value. And our rule of thumb for this is that for every 10 degrees we increase the temperature, the reaction rate will double. And so this seems like a small change when we're doing this in lab, but it actually has a huge effect on the reaction. The third thing is the geometry and the sterics. So our molecules have to run into each other in the right way in order for a reaction to actually happen. So we refer to this as either an ineffective collision if they're not hitting each other right, or an effective collision if they are running into each other right. So I like to think of this as putting on a glove. You can't just throw a glove at your hand and expect it to get on your hand. You actually have to put your hand into the glove and your fingers into the finger holes. There's only one way to get it on and have it be correct. And then one other thing that will affect our K value, affect our activation energy, is a catalyst. So a catalyst will speed up our reaction without being used up, and it does this by lowering the activation energy, which will increase our rate, so we'll increase that K value. So in the graph over here, the blue line represents the reaction without a catalyst, so we have a pretty large activation energy, and then the red line is representing our reaction with that catalyst. So there's a couple bumps here that's telling us that we needed more than one step to complete the reaction, but we do have a lower activation energy. And when we say it's not used up, that often means that they can be recycled. Sometimes they are still usable, sometimes they're not active after that, just kind of depends on what it is. When you go into biochem next year, you'll learn a lot about biological catalysts. So this is amylase. Amylase is in all of our bodies. It turns starch and glycogen into simple sugars. So this is a very, very large molecule. You can see a couple little benzene rings off to the sides here. The curly Q's are representing alpha helices, and then there's some arrows, yellow arrows down here. Looks like some red ones over here. Those are representing beta-pleated sheets. So this is showing us how that gigantic molecule is interacting with itself. but its job is to help us convert starch into those simple sugars. All right, this is putting everything together. So we're looking at the same energy diagram in both pictures, but what's highlighted in each one is slightly different. So in the first one, we're looking at how we can look at kinetics from an energy diagram. And with kinetics, we're focused on the reactants and then the top of that hill. And the energy difference between those 2 points is going to tell us how fast a reaction is occurring, or what that activation energy is. And when we're focusing on thermodynamics, we're looking at the energy of the reactants and the energy of the products and the energy difference between that starting and ending point. And that's going to tell us if our reaction is product favored, so if the products are lower in energy, as this one is, or reactant favored, if the products are higher in energy. So one energy diagram can give us a lot of information about the speed and the equilibrium. So here's a couple practice ones. The question says, which diagram represents each of the following? So we have reaction A, B, C, and D. If we look at these, we're going to decide which one's the fastest. So again, when we're looking at speed, we're looking at the height of that hill. So to find the fastest one, that means that we're going to look for the smallest hill. And so the one that has the smallest hill out of these would be option C over here. And the slowest one then would be the opposite of that. It would be the one with the largest hill. So that's going to be letter B. When we're looking for the one that is the most exothermic, now we're talking about the thermodynamics. And so the one that's the most exothermic is either going to be A or C. These are the two that are exothermic. And I know they're exothermic because the products are lower in energy than the reactants. A is much lower in energy in comparison to C. So A is the one that is most exothermic. And then for most endothermic, B and D are both endothermic because our products are higher in energy than our reactants, but B has a bigger energy difference. And then the last one is asking which one favors the products. So this one is our exothermic options. A and C both have products that are lower in energy than our reactants, so we could label those as product favored. All right, one more in this category to look at. We have two different energy diagrams. The first one on our left here, it says, what are the kinetic products? And the idea behind this is we have one reactant, A and B, and it could go down two different reaction pathways. One of it will form E and F, and the other will form C and D. And we'll start to look at this in our next chapter, especially as we look at reactions that are in competition with each other. And so when we say, which are the kinetic products, another way to ask that would be, which ones form the fastest? And for this reaction, E and F are our kinetic products because their hill, their activation energy, so this hill right here, is smaller than the other option, than the C and D hill. And when we say which are the thermodynamic products, we're asking which of these two is the lowest in energy. Low energy means more stable, so because C and D is lower in energy, those are our thermodynamic products. In the other question, or the other example here, same questions, which are the kinetic products? So we're looking for that short hill, and in this case it is the C and D option. And which are the thermodynamic products? C and D are also the lowest in energy. So in this case, we have kinetic and thermodynamic products of the same type. One more thing when we look at energy diagrams is that we can represent how many steps a reaction takes. So here's our energy diagram. We have our reactants on our left, our products on our right. each hill represents a step. So this is a 3-step reaction. The tops of the hills are called transition states. So these are the highest points in energy. This is the point where our molecules are in between breaking bonds and forming new bonds. So they can't be isolated. If you think of it like if you are jumping and somebody takes a picture of you, this would be at the top of the jump when you're in midair. So somebody could take a picture of it, but you wouldn't be able to hang out there and stay there. So same with the molecules. We can't isolate them at that point. When we're at the bottom of the hill, though, this is our intermediate. So this is the product of the first step and the reactant for this second step. This would be the product of the second step and the reactant for that third and final step. These are a little bit more stable. Sometimes they can be isolated, sometimes they can't. It depends on how stable they are. A real example though. So here we have our tert-butyl bromide, and we're going to react it with hydroxide. So now that we have this tert-butyl group with an alcohol attached. So it's a 2-step reaction. Here's the first hill of our first step. And so notice up here that carbon-bromine bond is breaking. And we know it's breaking because it's represented with that dashed line. So here I have it written out in reaction form. We have our dashed line to show that the bond is breaking. Another way we do this is that we put it in brackets and we put what's called a double dagger on the outside of it. So this tells us that it's a transition state. It tells us that it's not stable. It tells us that it's kind of in flux. After that bond completely breaks, we now have our carbocation and our bromide ion separately. So this is our intermediate. This is the product of that first step. And then we're going to use that carbocation down here as the reactant in our second step. So now our carbocation is going to react with our hydroxide. And again, at the top of that hill, we have another transition state. So this time the transition state is the bond forming. And so we still represent it with a dashed line because it's in the progress of forming. And we get that double dagger on the outside. And then when the reaction is complete, we can show that bond as a full bond. All right, last thing in this video is the Hammond postulate. When we look at those transition states, the bonds are partly formed or partly broken, depending on which direction we're headed, but they're not necessarily at the halfway point. So if our transition state is closer in energy to the reactants, then it's going to look more closely to the reactant. So if we were trying to break a reactant bond, instead of being halfway broken at the transition state, it might only be a quarter of the way broken because it's going to look more like those reactants. But if our transition state is closer in energy to the products and we're trying to form a new bond, then it might be 3/4 of the way formed at that transition state. So in an exothermic reaction, our transition state will look more like the reactants, and in an endothermic reaction, it will look more like the products. This isn't going to come up too much, and really when it does, I'll remind you of this. So this part's not a big deal. The important takeaway from this is being able to read those energy diagrams, being able to label reactants and products, transition states, intermediates, being able to know if it's exothermic or endothermic, fast reaction versus slow reaction. So really those last couple practice problems is where the focus should be. All right, that is it for our first video. Let me know if there's anything I can do to make this better for us, and I hope this helps. I will see you guys soon.